So welcome everyone to lecture 22. Okay, we look at submodular functions, some of the further properties and examples, and move towards optimization problems. Okay, so we got started with discrete optimization machine learning. We have kind of done some definitions and intuitions of submodularity, and we'll look at the modeling power today and the examples of submodular function and examples also of submodular optimization almost simultaneously before we move on to optimization algorithms. Okay, so we saw this. It's a recap of how we saw that general combinatorial optimization is very hard. If we had a special structure, we could do something more useful, and submodular functions therefore are interesting. They are also interesting because they have this diminishing returns property, which kind of will remind us of concave functions, but we'll also see that they do resemble convex functions in some way. Okay, so when you look from maximization perspective, they do resemble concave functions. And we also saw the example of number of distinct colors of balls in an urn as an example. That was a motivation. Okay, so the whole idea of diminishing returns. The more items you buy, the more the discount. And there are many problems, discrete labeling problem, summarization, where you want to place a sensor. Again, this is a recap, so I will move on to our homework problem. So before that, we saw this example of modular functions, right? We saw that modular functions are those which are both submodular, and the negative is supermodular. Okay. Well, negative is also submodular. That is, they are both submodular and supermodular. And basic idea is that because of this, you can decompose the function over a set to function over elements of the set. So they are akin to affine functions. Okay, again, recap. And we had a notion of monotone functions. You could also have monotone submodular functions. Set function is called monotone if as you grow the set, not in size, grow the set itself. Obviously, the size will also grow. The function value doesn't decrease. Okay. So function value should not decrease as you grow the function, grow the set. Right? A canonical example of this is the cardinality function, which is also, so it's monotone. What else is it from the previous slide? It's also modular. Right? The size of a set is the size of the individual elements in the set. Many other examples: influence on social networks, entropy. As you grow the index for the random variables, the function is monotone. In fact, it also turns out to be submodular, discrete entropy. Information gain is an example of a monotone function. Information gain, we'll see whether it's submodular or not, or under what conditions it's submodular. So information gain always monotone, but only under some conditions is it submodular. Yeah, and basically conditions are independence condition, conditional independence. Like naive base. So, but more about that later. Okay. So, oh, something is going. Yeah, slight formatting issue. So there's a homework problem I had left for you, right? Anyone thought about it? Are all monotone functions submodular? Not necessarily. Are all submodular functions monotone? In some sense, I already given a hint that information gain is monotone, but it may not be submodular. Right? I already said that information gain always is monotone, but only under some conditions is it submodular. But in general, if you want to answer such a question, you could actually construct functions. That's important. You could actually construct functions. Okay. Here's a function I have constructed. Very simple function. This function, what have I done? I've said just call f1a, fa, whatever you want. On the empty set, its value is 0. On the singleton set A, it's 1. For singleton set B, its value is 1. What happens when I add A and B, or have both elements A and B? It's 3. Does it look like diminishing returns? Huh? So in fact, this is a form of an attractive potential, right? We'll talk about this today. But what's the attractive potential? Potentially you're saying, oh, if A and B come together, suddenly their value is greater than just having A or B alone. Right? So the two are attracted to each other. It is monotone, it does increase, right? But it is not submodular. Try and construct. When you give a homework problem, right? Just try and construct. In fact, it's super modular, it's negative submodular. Okay, so if you try and plot it, it really has this not diminishing returns, but growing returns. So instead of becoming like this, it's like it's becoming like this. This is super modular. Yes, there are many. Entire class of modular functions. Well, modular functions are submodular. Right? Not all submodular functions are modular, but modular functions are all submodular. Just like they have equality instead of inequality. Yes, exactly. That's so. Be very careful. That's why attempt homework problems. You won't make such passing statements. Sometimes you assume you know the answer, but that's not the answer. In fact, this is strictly supermodular. Then it cannot be submodular. Okay, so if you want to call it strictly supermodular, because the inequality is strict. Its negative is strictly submodular. Okay, so I gave this example on the last slide. Conventional information gain based on entropy. It turns out that information gain is actually a difference of two submodular functions. So there are many differences of submodular functions which are monotone but not submodular. Difference of submodular functions mostly is not submodular. I mean, there are some conditions under which maybe, but generally it does not. The other way around as well, not every submodular function is monotone. So we'll see examples of diversity phase functions, log dead, disparity min sum. I mean, any diversity based function you will see it's not necessarily monotone. more diverse the points, doesn't mean that the volume or spread is increasing. We see that. Okay, so got an idea? So this is the general summary of function classes leading from the homework problem. You have submodular functions, you have supermodular functions, and at their intersection are these modular functions. Okay, so these are right at the intersection modular functions, which means they are both submodular and supermodular. Subset of submodular functions is monotone submodular functions. There are also lots of non-monotone submodular functions, and then there are some dispersion functions we'll see. There's like disparity min, disparity sum. Okay, right here it's this disparity min and disparity sum. Both of these are dispersion functions, which are not submodular functions. They kind of have nice properties like submodular functions. You'll see that. Okay, so let's look at some properties. And these properties will be very helpful in showing why certain functions are submodular. So the first is convex combinations of submodular functions. They're submodular. Okay, intersections with fixed sets, submodular. Unions with fixed sets is called conditioning. Union is called conditioning. Intersection is called restriction. So both of these are submodular. I mean, submodularity preserving. Complement functions are subordered. They're called reflection. And we look at two equivalent definitions of submodular functions. Actually, that I don't know if you have seen your assignment. Your assignment has that problem. Sorry? Yeah, first question itself. So obviously, I leave it to you as homework, but as assignment. But minimum and maximum submodular functions. It's a question mark. Think about it, right? So I'm going to leave that more like question right now. We'll see when it. Submodularity and convexity and submodularity and concavity. In fact, we'll also do information gain, which I will be mentioning here. Submodular mutual information function. Information functions. Which may not have always submodular property, but we'll see. Okay, so first property, convex combinations of submodular functions. Some of these are very, very intuitive. I mean, I don't think we need to even prove, right? If you have diminishing returns, like f of a union b minus f of a is greater than or equal to f of b union b minus f of b for a subset of b, now just keep adding. A and b are fixed. It's f1, f2. Add them. Inequality is preserved. Very simple, right? So if I have f IA union B minus FIA greater than or equal to FIB union B minus FIB for all A subset of B. All I need to do is multiply this entire expression with the lambda. That's it. The lambda is are all positive, right? So if I multiply the right hand side and left hand side both by lambda I and then add, this still will hold, right? And you can just take this, if you want now, you can act a little smart and say, oh, I can do this. So can I do this? I'll just take the summation also, or rather distribute the summation as well. Thing should hold, right? You got it? It's very straightforward. So I added this this distribution of the summation post factor. So it's closed under non-negative linear combinations. It's very helpful. For example, you could now have these lambda i's also replaced by probabilities, p thetas. Right? So a probabilistic combination of submodular functions is also submodular. Can that help you give rise to distributions? Yes, possibly. You can do multi-criterion optimization. The very exactly the proof technique I gave you is exactly what is pointed to above. Is that clear? Is a proof technique. Any questions? Okay, if none, then let's look at more properties. These are even simpler, I would say. I mean, restriction is just saying if you have a W which is a subset of V, and every time I evaluate S, F of S, now I call it F prime S, I'm going to do a intersection with W. W is fixed. So W is fixed. Or in fact, all of these are fixed. All the examples are fixed. So I'm going to do this intersection with a fixed guy. Very easy to show. I don't think we should. In fact, most of the times I'm not going to just give proofs. Right? Likewise, if you have W is a subset, but in this case, this W is again fixed. But you're doing a union with W every time I evaluate the function. Right? This is called conditioning. The first one was called restriction. It's called conditioning. This is also going to give you some modular function. And now a third one. In this case, I'm going to do basically take a complement. F prime of S is a submodular function F applied to the complement of S. That's what you do. F prime is the submodular function. So F is submodular in all these cases. Function F applied to the complement of S. Okay, so please note in all these cases, F is submodular already. It's declared upfront submodular. That's why we're able to do all of this. S is any subset of V. Obviously. Your ground set, very often we'll even skip V. V is the set of all possible elements. It's like saying Rn. Now, you can restrict it like I did in my counter example for homework. I restricted my set to these, right? So here I could explicitly call out and say that in this case my V is exactly A and B. This is universe of all elements. Okay, so all of these are submodular. Again, very simple to prove. As I said, there are two equivalent definitions of submodularity. One we have already seen is diminishing gains. This is what we also will be using often. But there's another property which I can provide the intuition about. Union intersection. For all A, B in subset of V, f of A plus f of B is greater than or equal to f of A union B plus f of A intersection B. So for modular functions, like for example, cardinality, what happens? What happens for cardinality? f of A plus f of B and f of A union B plus f of A intersection B. So A and B are in green and orange or whatever, right? But now I can highlight their union. So what is the union? This is the entire thing. Right, in that the intersection has been counted. Has been counted only once. Only once. So f of A union B. Here it's been counted. Now I'm adding f of A intersection B again. For cardinality. Right. So this part has come up again. So on the other hand, f of A plus f of B says I'll count A, also count the intersection along with A, count the B part different from A, also the intersection. So what is the inequality if f cardinality? It's equal to, right? So here you're saying no. In the case of submodularity, what we have been so far referring to as diminishing returns seems to have another characteristic. That if I add the two sets, a function on set A, function on the set B, then I'm getting something more than their union plus intersection. Okay. That's also kind of diminishing returns, but this is again your assignment. Okay. We will diminishing return. V should be bigger, greater than equal to. I mean, it could be one of the big. So question is, in diminishing regains, should the V be bigger than A and B? Obviously. Achha, oh, there's a mistake here. Oh, yeah. This is A subset. Yeah, I made a mistake here. Or A subset of B, subset of B. Thanks for pointing that out. Whereas intersection, union intersection doesn't require that. At any two sets, A and B. Okay, let's look at maximum. Maximum of a submodular function, is it submodular? So here we have seen for convex functions. What did you see for convex functions? What did you see? If I had this function and say this function, then what is a maximum? This, right? It's convex, we have seen that. But maximum of submodular functions, which seem to be like concave functions, and here I've shown them as concave functions, doesn't need seem to be submodular, right? In fact, maximum of concave functions is not concave. Okay, so I would say in fact, just like maximum of concave functions need not be concave. In general, of course, if it's a linear function, it's concave. In fact, the other way is also you can also say the minimum of convex functions. If I take the minimum of these two, is that submodular? If I take the minimum of these two, minimum of two convex functions, is it convex? Huh? No, convex functions need not be convex. Okay. So maximum of submodular functions like concave functions doesn't appear to be submodular, right? If you take the max here, that's what we have shown. Take this part in green. It doesn't appear to be submodular. The diminishing returns is lost. Like going up and then down again, then up. Right? It's not always shaped downwards. Sometimes it gets shaped upwards. So then what you might be tempted to say? What would be your immediate temptation? They look like diminishing returns, so their max is not. They are like concave, so obviously their max is not expected to be submodular. Max of two submodular functions. Do you think the min of submodular functions will be submodular? Yes. How many of you feel the min of submodular functions will be submodular? You feel great. Any other show of hands? Let me ask the question. How many of you feel that the min of two submodular functions will always be submodular? So more, anyone else? You don't feel so? You don't think so? Anyone on the call? Show of hands. So you feel it's not going to submodular? Yes? Not sure. Okay. Okay. So you feel probably because they behave like concave functions, right? The issue is that even though we wish it were, that's not the case. They don't even behave like concave functions consistently. And here's an example, again by counter example. So f1a is 0, 1, 0, 1. f2a is 0, 0, 1, 1. Okay. And you can check f of b minus f of empty set is 0. F of a comma b minus f of a is equal to 1. What is f? F is this minimum. Right? So this is less than, right? This is not showing diminishing returns. So for this reason, I mean, this is the counter example. This counter example is good enough to show. It's a proof that it's not submodular, or there exist cases when it's not submodular. Right? But there's something interesting here. Okay, if I ask you a question, okay, what happens is F1 and F2 is there any inequality between F1 and F2 in general? Is F1A always less than equal to F2A, or is F2A always less than equal to F1A? So let me ask a kind of leading question. What if we always had F1A or F1 whatever argument less than equal to F2 for the same argument, or we had F2 the same argument less than equal to F1, one of them consistently, which is not the case here, right? This is not consistently, one is not consistently greater than the other. You see the inconsistency here, right? Here F1A is equal to F. Here F1A is greater than. Here F2A is greater than. They are not consistently one greater than the other, right? It turns out that your intuition holds in that case. Okay, so some credit to you. Right, so sorry? Right, correct. We'll come exactly. right? So obviously F will be submodular. Since it will collapse to one of them. Okay, so no marks to me for making a very obvious statement. But let's make a slightly more. Oh God. So network problem. I have to go to hotspot. Hello. How many? For how many minutes have you missed? Because there was a, I think, network outage. For how many minutes did you miss the class?
Sir, we didn't miss, sir. It was okay.
Sorry?
We didn't miss. Yes.
Oh, you didn't miss much, huh? Okay. I can continue, right?
Yeah.
So what if we always had one of these? Certainly, there'll be F will be submodular because it will collapse to one of them. But let me ask some slightly more interesting question. What if F1 minus F2 or F2 minus F1 was monotone? Okay. F1 minus F2, obviously argument with arguments, or F2 minus F1 was monotone. Again, you note that we don't really have monotonicity here either. Do we have monotonicity here? F1 minus F2, as I keep doing the set. Do we get monotonicity? Right, this is not monotone. So I keep adding elements, increasing F1 minus F2. Right, it's 1 minus 0, A. At A. At A, B is 1 minus 1. But at B, it is 0 minus 1. Right, so F1 minus F2 at B is minus 1. Sorry. At B is okay, it's A. Is 0. Is 1. And F1 minus F2 of A comma B is 0. This is the problem. It's not monotone. Right? So it turns out that if F1 minus F2 is monotone, then min of F1 comma F2 is submodular. So there's slightly more than just one being always greater than the other. Is that clear? So yeah, no proofs. I think I'm trying to provide some intuition. Sorry? What if F1? Yeah, either way. Okay, so question was, what if F1, F2 minus F1 is monotone? F1 minus F2 or obviously F2 minus F1 is monotone. The symmetry is there. The next very interesting property is that concave over submodular functions is submodular. Concave over monotone submodular functions are submodular. And the simplest example is like, let's say I have a size, cardinality, size of A. That's modular. What about square root function? What is the nature of square root? Is concave. So what does this imply? According to this, square root of cardinality is submodular. So feature-based functions we'll see are submodular. Obviously, this also is not limited only to modular functions. Given a concave function g and monotone submodular function f, then g of f of s is still submodular. So this also holds for monotone submodular functions. It's if you have positive modular function m. Okay, so this is the interesting thing is it's not just modular. A is monotone, it's positive. So that's important. You need it to be monotone or positive submodular. Specifically because if you have a positive modular function, it's going to be monotone. Okay, so positive they are always monotone. So feature-based functions we'll see are submodular, right? For example, if you're some kind of a network, right? Deep neural networks. So if you create if there are concave functions which compress, then you can basically get submodular functions. And doesn't hold if m is negative, right? For example, the modular function is negative. It should be positive because then only you can have monotonicity. Okay. So another case, madam. In fact, we'll see a stricter result later on. We'll see positive modular. Because positive modular. So question in the second line, should it be positive submodular? No, monotone submodular. But positive modular functions will also be monotone, and they will be also submodular, obviously. Positive is not negative. I mean, greater than 0. Greater than. Yeah. But we'll see a stricter relation between concavity and submodularity later on. See a related. I mean, it's a related stricter relation in terms of composition. But we'll see that there's a stricter if and only if relation. Stricter, when I say stricter, I mean if and only if something is submodular only if something is concave. So, but wait for that. But I think in that case, in that setting, I will recap this discussion of ours. Sorry? So you can say it's non-negative. Yeah, that's a good point. We can, yeah, let me just change this, non-negative. Okay. So with this, you understood a bunch of intuitive properties, compositions, etc. Because we have done so much for convexity. We are not going through all the results again, but it should be very straightforward to understand. Right? I mean, this makes sense also because diminishing returns, that's explicitly carried forward here. But it has to be increasing, otherwise that diminishing returns won't necessarily show up when you apply on a monotone function, on a modular function, submodular function. Okay, so here are some instantiations, and we'll look at some of them. Um, yeah, we may look at them in slightly different order, but they have representation functions where you're trying to represent some points, say facilities, some food outlets which you want to set up such that those food outlets cater to the population. That's a facility. That's a representation. We see graph cut also, saturated coverage examples. Diversity functions, which basically look at how diverse spread out the points are. As I said, these are not submodular. This functions, especially min and sum, they are not submodular. Though behave similarly, very similar, very closely. Okay, and also graph cut also submodular under certain conditions, not always. It's like a summary. Okay, so coverage function, set cover, probabilistic set cover, feature based functions, these are largely submodular. Try to cover a bunch of concepts as against points. So representation functions are about representing points. Whereas coverage functions are about representing features. Covering features, attributes. So that distinction will help appreciate their definitions. And also importance functions. How important is something? Cardinality of a set is an importance. That is modular. Information functions like mutual information, they're submodular under certain conditions. I talked about it earlier. They may be monotone, but submodular under some independence assumptions. Entropy, on the other hand, discrete entropy is always submodular. Okay, so that's always submodular. I will not mark whatever is submodular. I understand. Okay, then the other discounted cost functions, clustered, concave, or modular functions. I told you, concave or modular, we expect it to be submodular if the modular function is monotone, basically, or non-negative. Cooperative cost. If you look at the homework example was a cooperative cost example. But there are some modular cooperative costs as well. Okay, so that was not necessarily, that was a super modular function. Okay, and then neighborhood functions, bipartite functions. We'll see some of these complexity. These, I would like to point out that these are not functions we'll use too much. These are more interesting from a minimization perspective. Which we will not deal with in the class. Okay, but we'll nevertheless talk about these functions. Okay, so let's look at minimization. In fact, I'm beginning with the reverse. We'll discuss the reverse, almost in the reverse order. So let me just make a note of that. We will discuss these now and not revisit them. Okay, that's why I'm doing the reverse order, because we will not be interested in building upon them so much. So what is the first? Again, I remind you, we are looking at the discounted cost function and complexity functions. Okay, so what are these? So first is cooperative cost. I'll give examples of each of these more detail, but you can see this the reason it's submodular is that you're looking at a set A and how much, let's say this is my set A, right? Let me shade it in a different color. So let's say my set A consists of these points, which are marked 1, 2, 3, 4, right? So what I'm doing here is I'm looking at the intersection A has with P1. So A has 1 and 3 intersecting with P1, right? A intersection P1 is 1, 3. A intersection P3 is 4. A intersection P2 is 2, right? So Ri is like the reward cost associated with Pi. So let's say R1 is 5, R2 is 3, so R3 is 3, and R2 is, let's say, 1. It's basically saying how much importance to associate with each. So I look at A intersection Pi, and for every point in that set, for example, 1 and 3 intersection with P1, I'm going to assign 1. That's what it's meaning. So this function, what you see, the blue part, what is the nature of this function? Summation over J in A intersection Pi. What is this? Summation over Ri. It is modular. This is totally modular. The square root of that is submodular. And then summation, we have seen non-negative. It's submodular, right? So then the simple reason is non-negative sum of square root of modular functions, in simple words, of non-negative again. Okay, so that's important, is submodular. Okay, so it's important to note that each of these Ri should be greater than or equal to 0. Ri should be greater than or equal to 0. Obviously. Second example is attractive potentials. If you have, I'll look at the examples next slides, but why they are submodular or under what conditions they are submodular. So attractive potentials, the word here basically means that you have the energy associated, right, with Eij with 1 and 1 should be greater in some sense. Right? I want 1 and 1 to be attracting themselves more. In fact, on one line. So you would expect Eij 1 1 plus Eij 0 0 should be greater than Eij 1 0 plus Eij 0 1. That's what we mean by attractive potentials. Okay, that's exactly what we mean by attractive potential. So as long as they're attractive, then you can show that this function is submodular. I'll give a reason later on. Okay. Intuitive reason mainly. A third use case is complexity. Let's assume that you're trying to build some translation corpus or language model or a speech corpus. But I want to make sure that let's say I want some toy model, right, which I'm going to build on this. So my toy model, I would like to build on a small vocabulary. So what you see on the right hand side is like the vocabulary. This is a vocab. So I want the, let's say I want to all these are minimization by the way, right? I'll give the interpretation later on, but I want a low vocabulary model which covers the entire corpus. So that's complexity. But let's look at each of these in some more understanding. So let's look at the first, which is cooperative cost. Okay, what is the intuition? The first one, let's say it's breakfast time and you want to basically buy certain items. You want to buy milkshake, you want to buy some muskmelon, you want to buy some sandwich. Now you know that there are some locations where you get these. You get something in market 1, something you get in market 2, right? Some things you get in market 3. Now, would like to get all of them in one place. So you want to minimize the cost of procuring these goods. The cost is time to shop and price of items, both. Maybe if you go to one market, they will give a discount as well, right? So time to shop, let's understand the intuition for time to shop. Right? If all items are procured in one or few markets, the time to shop will be less, right? On the other hand, the price of items, again, they can be discounts. So if all items are purchased from a similar market, right? The smaller, the more the number of items you manage to purchase in a single market from, more is the discount possibility. So this is an example of minimization. Right, so you see these two parts. Time to shop, cost, there's a cost part. So there's a kind of fixed overhead. If you go to one place, I have to anyways, and obviously within that market it will take some time. And the number of items, 2 items. But then again, you can look at discounts. Number of shops plus number of items, in some sense. Actually, this should be so in the first place, you're buying basically one item. The second place, you're buying 2 items. So this turns out to be submodular. I mean, I'm not really, I think I have not really accounted for the discount possibility. So I should just change this to something wishful. I haven't done that. We have offered the same cost, right? So more specifically, more generally, this could be done. I haven't done this. Oh, sorry, can't see the color. Okay, so this not shown here. You could do that in general as well. Okay, so that's exactly what I said. F of A is summation over all the partitions P1, P2, P3 of the sum of all the elements I buy from each partition, but with a diminishing part, the square root part. Like next example, second example. So that's clear, right? Second example is attractive potentials. So here, let's say I want to segment an image. And imagine that all the ones correspond to those which are outside the image. Okay, this is 1. All the blacks are 1s. All the whites are 0s. Okay, 0, 1. graphical models, if you've done a course, then you've come across a problem of segmentation. So I want to look at what pixel is befitting a dog. That's the energy part, right? EIXI is just saying if pixel high, if pixel xi does not, or actually we want to reduce, right? So if pixel xi does not resemble a dog, it doesn't look like any part of a dog, for example, that pixel xi. So that's okay, that's not very, I mean, that's fine, that is important, but that's just modular. This is a modular part. But what is going to draw our attention is the second part, the submodular part, or under some conditions then it's submodular. This is the partition part. And here we are basically saying that exactly what I brought up earlier. If Eij, sorry, I made a small mistake there. I should have been the other way. I mean, I was saying that Eij11 plus Eij00 should be less than equal to energy. Energy of similar configuration should be less than the energy of different configuration. It was less than equal, right? I made a mistake. That's the same thing we are saying here. We are saying that Eij10, if I go from 1 to 0 here, 1 to 0, these are all 1 to 0, right? Or 0 to 1. The cuts should be greater than or equal to the energy associated with being within a region. Okay, so if I'm just within a region, I'm better off. This, interestingly, the fact that there is submodular, you can associate it with the second property of submodularity. F of s plus f of t is greater than or equal to f of s union t plus f of s intersection t. Submodularity can be proved using the second equivalent definition. That's why we brought up the properties up front. Which one? This is correct. Energy, we want to minimize energy. High energy. So think of, Ising models. Ising models, if you have electron spins, what would you like? High energy or low energy configurations? Right. So therefore, if you have similar positives, right, sitting together, then you'll have, okay, that's a different thing, but basically negative of that you have to take. So you'll have high energy. So here you would like the similar to come together. The idea is the same. You want low energy configurations. So this is low energy. Okay, now you can think of this having only the first component as basically S. Only the first component is basically S. Having only the second component on is basically T. Right? And having neither of the configurations is S intersection T, being empty. Having both configurations here is the union. Okay, so you can do this mapping. Simple mapping, you can show that this is submodular, such a function. If this property holds. This property is submodularity basically. I mean, so it's the same thing basically. So function is submodular if. So E is, so let me just explain. E is submodular if the property It's called spatial coherence property on the RHS codes. That's OLED. Is this clear? Basically, it's like saying it's just, so instead of saying submodularity can be associated. Or rather spatial coherence properties. That's what I meant. Is it okay? Simple association. Third example, complexity functions. So as I said, you may be often interested in a low vocabulary. So, oh yes, true, that's, let's say I want only 50 words in building my language model. What 50 words should I be? So I can look at notion of complexity. Each x is going to be covered by the gamma, f of a is gamma a. The gamma x is the complexity induced by the subset of words. Kind of measure of, it could also be a measure of size. So we'll not go into this. This is again, this can be proved to be submodular, very simple, and often this is the concave over modular. A possible choice, which is also a popular choice, of gamma is, say, square root of the size of A. Right? So I want to minimize the number of points I select in A. So now look at the maximization aspects, and again, some of these we'll prove, some will just give intuition. So these are all maximization perspectives of modular functions. If you want to have sensors to be placed, where should I place the sensors? I want to place sensors such that I cover the area well. Right? Like I want to fit ACs in this room. Obviously, you don't want all the 3 ACs sitting blowing here, right? You want them to be distributed there so that there's coverage. That happens to have, it's very obvious in this, right? You have diminishing returns. If you put too many in one place, more than next AC that you add, you'll all be pushed out of the room, right? You'll run away. So diversity, the more the spread out, the more the points are diverse, larger will be the volume of the area, let's say polyhedron that encompasses these points. So that's log det example. Information, if I'm trying to select features, okay. So this is like volume example. This coverage example, very obvious, sensor coverage. Example here is features. If I have to select features such that I represent the class as well. So features are, for example, features are, say, x1, x3, conveying max information of the class label y. Right. So this, I want to select those in green, which are going to convey max information. Representation. I want to pick up my points, the green, the pink, and the blue, which will be basically by A's, right? So let's say this is, all are J's. So this is 1J element of A. This is another J element of A in blue. And basically now each of these J's will be closest to one of the points in the ground set, the entire set. So I's are basically ranging over all the points in the set. So I want, and then SI similarity. Okay, so Sij is saying similarity between the ith point to some say jth cluster, this cluster representative. So find the most similar cluster representative for each point and sum this across all points. Example, right? Find the most similar, or rather find cluster representatives such that the most similar cluster based similarity summed across all points is maximized. Okay, I'll see each of these now a little carefully, but this is just to give you an idea. This is a gamut. So let's start with representation functions. That again multiple options here. The first one I discussed was what I showed there. Okay, so what we have here is a similarity kernel Sij. Sij is saying, okay, how similar is point 5? Okay, similarity is like 10. Self similarity will be very high, right? But you could have say 5, and some may be very less similar to each other. The diagonal will be of course high. You have seen kernels, SVMs and all, right? So it's a similarity kernel. Diagonal could be diagonally dominant. So based on this S, what do you do in representation functions? You're saying I'm going to now, let's look at facility location. In fact, I'll prove that facility location is submodular. So what is facility location saying? Okay, I want to look at for all points I exactly what I wrote. Let me just copy this part. This is exactly what I wrote for facility location. And this is represented here. This is the example. Find cluster representative. So I'm going to find these cluster representatives in the form of these facilities, factories. It could be malls. These are cluster representatives. Now these cluster representatives may not coincide with the people, right? But that's okay. So I want to find the cluster representatives such that all the points, which are all the people here in different locations. Okay, so these are all people. These are all points. So I want to find the cluster representatives such as the most similar cluster. So now look at, let's try and associate, right? Obviously, every group of people is not going to visit every mall. You don't have people from Bhopal visiting Mumbai malls. They need local malls, right? So then obviously what I'll need to do is, yes, people are all there, but I'll need to find the binding. Okay. So there's a lot of clusters across all points, but what I want to do is the most similar cluster part. Okay, so what's the most similar? This is the most similar cluster. Let me make it darker. This is the most similar cluster. This is the most similar cluster. These will go together, right? But now this guy will go here. So I can just do an association. Now this guy will go here, and so on. Yeah, I hope I have drawn all the lines. Okay. Right, so based on this, I want to, now this is the SI, max over I, right? That's exactly what max is doing for you, right? Max over K in X of SIK is just finding those pink edges. Sparse in the sense you don't sparse set because you're not looking, you're not picking all the edges, right? Is this clear? So this is facility location. Now facility location might not land up covering all the points. If I have a budget, let's say I can only set up 4 malls. I may not be able to cover, Dharamshala. I mean, maybe 4 malls because there will be very few people represented in a remote location, right? That's exactly what happens here. You'll find that outliers are not represented. I mean, outlier itself is a very relative term, but no, certain points may not be represented. Outlier-like points. Obviously, we don't want to say any location is an outlier. Outlier-like points might not get represented. Yes, you can see that in the figure on the right, that we have only representation for some of these points. I mean, for all the other clusters. So you have a representation from this. These are all represented. Because there are more points. So the number of points close, the more there is voting for that candidate. Saturated coverage. Now, saturated coverage, what is it doing? It says that instead of a max, okay, look at the difference between facility location and saturated coverage. Here, instead of a max, I'm looking at a sum. Sum of similarities. All the points are contributing to every point in X. X is a subset that I want, right? So, a cluster representatives is in X, right? So, in the case of saturated coverage, every point in X is being voted to from every point in V. Okay, so every point in ground set E is voting through a similarity function for every point in the subset being considered. So there's kind of, no max. There's no max. There's no sparsity. No sparse set selection. But I say, well, you can vote up to a limit alpha. Right? Beyond alpha, I don't count your votes. And that limit alpha is what creates the submodularity. Otherwise, it would be modularity, right? This part is itself modular. But up to a limit alpha is what brings a twist in the story. Okay, so this makes it some, I mean, this otherwise is modular. The part in yellow is modular, but this part makes it submodular. Is it clear? Yeah, that's a saturation. Outliers, oh, you're saying outliers will come in, it depends on the alpha value, right? So question is saturated coverage should not capture the outliers. So if you set a very low value of alpha, and yes, even if very few people vote for you, you're fine. Actually, it depends. I mean, you'll have to think a bit more. It depends on the budget, because if, but yes, it potentially saturated coverage might pick up outliers for some suitable value of alpha. It's a good point. And that's it's also for every point there's a different contribution. So that's also note that. Okay. So you want to put alpha I, that's also fine. There's an alpha I. It can be independent of I, it can depend on I. Okay, so the basic idea is clear, right? Okay, graph cut on the other hand, what it's trying to do, I think, I don't know if I probably have slides on each of these. Yeah, graph cut. Graph cut, let me go to the next slide, that's better. Too much crowding. Graph cut says, so if I have a set X to be subsetted, and of that I'm trying to identify a subset. This is a V, this is an X, this is the entire set V, right? So graph cut says that I'm going to look at the how well the points in X are representing the points in V through similarity. But there is a slight trick. So I want to look at similarity of X to V, but I want to discount for the self similarity. So there's a self similarity which I want to discourage. I mean, X will always represent X itself well, right? I mean, look at the example we showed earlier, diagonal dominant. Let me just copy this part, right? We showed this diagonally dominant case, right? So if it's diagonally dominant, obviously points in X will represent themselves well. Let me in fact use the same color coding. So what we're going to do is, I have the X. Let me actually use green only. Okay, so I have my X, and what I want to do is I'll say, oh, actually let me, I want to make sure that the self similarity of X to itself is being discouraged. So discourage which is reflected through diagonal dominance. Is that clear? Let me just type, it's just getting too messy. Okay, so modulo that, what you're trying to do is maximize the similarity of points in X to the points in V. So that part is being encouraged. So this entire similarity, how well is X representing V? That's the second. That's this part. In some sense, X, I in V, X in V, but I'm doing a subtraction, right? So this is a representation part, a sum overall. So it's summed, not max. Very similar in to the saturated coverage case. Just that you don't have a min, that's there's no alpha I. But here what I've done instead is I say, okay, I'm going to subtract from that this part which is self similarity. Okay, now lambda should be at least how much? Lambda is discounting, right, for self similarity. Lambda can lambda be less than 1? Does it make sense? Because look at the first component, summation over I, summation over X, summation J over X. So lambda should be at least 1. But it turns out that it is not monotone submodular when lambda is less than 2. So if lambda is greater than 2, it's also monotone. Okay. So you don't want to kind of totally suppress, that's what it's saying, right? You don't want to totally suppress self similarities. Points in X should represent themselves well, but not more than they represent the points in V. So you can put that as a simple message, right? Points in X, huh? Yeah, lambda is equal to or greater. Okay. Yeah. Oh, you're saying yeah, you're right. It is submodular otherwise. So represent E points in V minus X, so V slash X more than they represent themselves. That's basically what we are trying to say here. Okay. Let's try and prove. Okay. So these are I've already given this example. The graph cut example I've given here. So this would probably help you. So you're trying to identify a set of points X such that they maybe the points here in green, you could think of them as one potential. They represent the other points well, while discounting for self-similarity. Okay, so let's look at the facility location, which is in the center. I'll show its proof. The others are not very difficult. Saturated coverage is actually very simple. Okay, so the proof is idea is as follows. So something has gone wrong. Something has gone wrong totally in the formatting. Okay, I'll try and see how to fix this. So yeah, I hope you can read this. The definition based on diminishing returns for all A, B in a subset of V. Okay, so I mean, more or less is okay. Just some things are going a little wrong. Okay, so this is the definition we know, right? F of A union V minus F of A is greater than or equal to F of B union V minus F of B for all A, B subset of V, where A is also subset of B. Now let's define this conditional gain. The conditional gain is F of V given A minus F of A union V minus F of A. So it's a very compact notation. Okay? Conditional gain. So another definition we can give in terms of conditional gain is saying that F of A, F of V given A is greater than or equal to F of V given B if A is subset of B. Basically saying the conditional gain with A is greater than the conditional gain with B. So now let's consider this part below is where the proof begins. So far I've just defined just some definition. So this part is where we begin the proof. Okay, I'm going to give you a beginning here and you have to help me complete. So consider Fx is facility location max over k in x sik summed over all I in b. And I have now defined gix such that this gix just corresponds to this component. I don't want to deal with the entire function. The whole idea is deal with it in parts. And that's exactly gix. So I can just plug in gix. Basically for any single point, I just find the most similar x, right? And then a point k in x and plug that in. How do you complete this proof? And hint I'm giving is use conditional gain, which I've already provided, and use this gix. Can you complete the proof? please try. Can you complete a proof of submodularity? Just give me the basic idea, even if you don't want to write the whole thing. Of f based on GIs and use of conditional gain. Any thoughts? Anyone on the call could also please suggest answers. Oh, we already 5:30. I didn't realize. 3:30. Okay, I'm going to leave this as homework for you to think about. If you are pretty much there, right? So this is actually a homework problem for you, and that will also kind of prepare you for your assignment. Yeah, in assignment you have some proofs to be made, right? So let's do this one thoroughly. I will not do many more. This one we'll do thoroughly. Okay, so I'll leave it to this homework problem. Okay, thanks then. We'll meet again on Thursday.